Well, it's great to be here. Thank you very much for the invitation to come speak. This is my first encounter with the Foresight group, and it's fascinating already. I'm going to talk a little bit about the search for extraterrestrial intelligence, what we call technosignatures. And just by way of introduction, I'm the director of the Berkeley SETI Research Center at UC Berkeley, close by here, and also the principal investigator of a project called Breakthrough Listen, which is a 10-year, well, now 15-year, thankfully, $100 million search for extraterrestrial intelligence sponsored by the Breakthrough Prize Foundation. Over the last couple of decades, we've learned something really incredible about the universe. Something maybe that some of you might think is obvious in hindsight, like a lot of sort of good ideas, and that's that the galaxy and indeed the universe is absolutely awash in planets. A few decades ago, it was thought that perhaps our solar system was an anomaly, that the dynamics involved in planetary system formation would expel planets very easily from their host star. But now we know that that's not the case. The average number of planets per star is greater than one. And we think that something like maybe 15 or 20% of stars in our own galaxy have a planet something like the Earth, at least in terms of its equilibrium temperature. But the question I think most of us ask when we think about all of these planets out there, are we alone? Is there any other life out there? For the moment remains a mystery. The galaxy and indeed the universe is very much like the dark forest. We look out there and we assume that perhaps there's life there, but for the moment we don't know. There's a fantastic illustration of how we could go about looking for life beyond the Earth. It was brought to us by the Galileo spacecraft, which was launched in the later part of the 1980s. A group of astronomers led by Carl Sagan took the Galileo spacecraft and actually pointed it back at the Earth to see if we could use a spacecraft like Galileo to detect the fact that there was life on our own planet. And it was fantastically successful at doing that. It used a spectrometer to measure the constituents of the Earth's atmosphere, and it found what we now call a disequilibrium chemistry, a chemistry that appeared to only be possible if it was driven by some kind of biological process, the presence of oxygen and ozone and methane, etc. I should point out that this is not an obvious conclusion to draw from this measurement. In fact, it takes a rather detailed modeling of the relative abundances of all of these constituents in order to come to the conclusion that a biological process is driving this. And moreover, this is a fantastically difficult measurement to make on extrasolar planets, on the atmospheres of planets around other stars. And in fact, even the best telescopes that we have now and the best telescopes we could build in the next couple of decades could only make a measurement close to this and possibly be able to infer the presence of biology, maybe around a small handful of extrasolar planets, maybe 10 or 20. The Galileo spacecraft also used an imaging spectrometer that was able to measure something that we call the red edge. This is the selective absorption of optical light from foliage, from plants, on the Earth, and the great increase in reflectance when you get into the infrared. This actually a much stronger indicator of the presence of life, but a very, very difficult measurement to make on extrasolar planets. And together we call those things biosignatures. But it also detected something else that we now call technosignatures, which is the presence of very narrowband radio emission. This is frequency versus time here, and you see there's a concentrated band of emission around about 5 megahertz or so. And as far as we know, there's no natural process that could create radio emission that looks like this. This is an unmistakable indicator of technology and thereby intelligence, as far as we know. And moreover, it turns out that it's actually the most detectable thing. I'll talk about this a little more as we go on in the slides, but this is something that we could detect potentially from many billions of nearby extrasolar planets. So it's, I think, worthwhile to think a little bit about why it is that these kinds of radio sources or other kinds of sources of electromagnetic radiation are unique relative to natural sources, and that's because they compress energy in either time or in frequency. This is something that natural sources tend not to do. Things like astrophysical masers can compress signals in frequency a little bit. Things like pulsars and gamma ray bursts, fast radio bursts, can compress energy in time. But only artificial sources can occupy this very particular part of this sort of parameter space diagram, really a cartoon that I've illustrated up here. And this is really the fundamental property that we use in 99% of SETI searches. I'll also point out that there are a lot of other kinds of coherence that we could imagine. Polarization, spatial coherence, coherence in various quantum mechanical properties of photons, et cetera. Or indeed any other information carrier. So if you've been following the SETI field a little bit over the last few years, maybe you've seen sort of one or two of these telescopes, maybe the Allen Telescope Array, or you knew that the Arecibo Observatory was being used for SETI. But today we've seen a fantastic increase in the number of telescopes that are being used for SETI. As we sit here today, really, most of the world's radio telescopes are being used for SETI research, most of them by our group, and indeed optical telescopes and space-based telescopes as well. The field of SETI has really come into its own as a part of the broader academic research ecosystem. And I already mentioned this, but if you just as a thought experiment, if you take the largest single-dish radio telescope we have, the FAST telescope, and you ask the question, how far away could it detect the most powerful radio signal that we have, the Arecibo planetary radar, that number's about 20,000 light years, which means that an Earth-level technosignature, an Earth-level civilization, could be detected on hundreds of billions of extrasolar planets. Just in my last slide here, I just wanted to point out something very, very interesting about SETI, a bit of a historical anecdote. So about a century ago, the very first modern SETI experiment, as we call it, was conducted when an astronomer named David Todd got together with an engineer friend of his named Charles Jenkins, who had designed something called a radio photo message machine, which was in fact a very early TV receiver and TV transmitter. And they pointed it at Mars to try to see if they could detect Martians. And I put this up here for a few reasons. One, because less than a century ago, the kind of state of the art in this field was to point a TV receiver at Mars, but also to show that there's a long history of collaboration between astronomers and engineers. In fact, the field of SETI is really a conversation between engineering and astronomy. And I think what better sort of landscape for those conversations to happen than this meeting. So I'll just leave up these kind of discussion points and take questions.
Wonderful. Thank you so much. If Carol's here, if you want to get mic'd up for your presentation, that would be wonderful. And we'll take questions. Yeah.
What do you say to the, what do you say to like the DIS, that looking for radio transmissions from advanced civilizations, advanced compared to us, is like looking for smoke signals from us?
Yeah, well, I mean, I would make sort of two comments to that. One, I accept the DIS. I think it's a fair point to make. One thing is that smoke signals are not detectable across interstellar space, whereas electromagnetic emission is in fact detectable. So just purely as a factual matter, if there were a civilization, something like our own, on a planet in orbit around Proxima Centauri or one of the Alpha Centauri systems, we would be able to detect it. At least in the next maybe decade or so when we get slightly more sensitive radio telescopes. So we could in fact see it if it were there. And the other thing that I would say is that these are the very best ideas that we have today. And we have no reason to believe that our understanding of physics is anywhere near complete, any more complete now than it was 100 years ago or 1,000 years ago. So we, as Jill Tarter loves to say, we reserve the right to get smarter.
Hi, I'm Mike. A question I've always thought about this. For the record, I think this is super cool and that you should do it and you should have all the money.
Thank you.
Do you think that the public will care? And do you think that, I think that we could discover, I think it's very likely in the course of our lifetimes we discover biosignatures on exoplanets. Do you think that it will land with the public? Do you think that it actually changes anything about public consciousness? I
think it depends very much on the specifics of the detection. If it were just a narrowband radio signal, like say a 1 hertz radio signal, at 1.5 gigahertz or something like that, I think that it would take an awful lot of time for that really to kind of imprint on, the human psyche. For one reason being that a lot of theorists would come out with some idea for how that could be created with some natural process rather than an artificial one. Now if an interstellar object shows up and we look at it and it looks like it's made of metal, and we send a probe up and we check it out and it turns out to be a flying saucer coming through our solar system, well then I think the reaction would be very different.
Well, that's related to what we were last night. He said biosignature, and you pointed out biosignature does not equal technosignature, and the cultural implications would be quite different.
Yeah.
Okay, wonderful. Maybe, did you want to make a final comment?
Yeah. Maybe I'm not reading this right, but how come you're not having among your detection strategies high energy activities like starship propulsion or terraforming activities, artificial suns? These are the kinds of things that an advanced civilization might do that would be loud.
Yeah, so in the case of directed energy propulsion systems, our searches would be sensitive to those. Those are generally spectrally confined. They're transient, probably, rather than continuous. But our searches would be sensitive to those in the radio or in the optical, something like Starshot. The other examples that you gave, I would say that those kind of fall into the sort of anomaly detection sphere, like looking at astrophysical objects generally and looking for the ones that kind of stand out. And we also do that. And that's much closer, I would say, to sort of traditional astronomy and astrophysics than SETI, but we pay attention.
What is your challenge? Something that you want others to
yeah,
solve?
no, definitely. So how can we conduct a sensitive search for, what should I call this, cosmological constant bleeding?
Sure.
A sensitive search for cosmological constant believing?
Bleeding.
Bleeding.
And you can use lambda.
All right. Well, I'll fill this in as we go. Called constant bleeding. Wonderful. Okay. Thank you so much, Andrew. This was wonderful.